Okay, I'm going to finish talking about variability, and we will be calculating the standard deviation in class. There's two ways to do it. There's a conceptual and a computational formula, but I want you to see how it's calculated because that is important. And in statistical analysis, in articles and presentations, all researchers will have to present one measure of central tendency and one measure of variability. And that's because they work together. Remember, the central tendencies tell us something about the central part where all the scores are, and the measures of variability tell us something about the spread of scores, how wide they deviate. Again, think of deviations, how far they deviate from the mean. So sometimes variability is examined because the central tendency scores are pretty often distributed differently. I'm not making myself clear here, but let's just say that if you used a mean, you would have to report the standard deviation with it. You always have to report one measure of central tendency, one measure of variability. Rarely do you ever do the median and the interquartile range. If you look at any research, and maybe I'll bring in some of my articles, if someone presents the mean, then it's basically by law. It's a statistical law, I think, that you have to present the standard deviation. And it makes sense because both of those incorporate every single score in your data set. And so we're going to calculate one in a couple minutes after I finish standard scores. But just here's your definition. I better define standard deviation for you pretty quick. It's the average of the spread of scores around the mean. It's the average of the spread of scores. So it takes into account every single score. Every single score is subtracted or added from the mean to measure its variability. So it's very powerful. So every single score impacts it. And if I have a slight change in some scores, that'll affect the mean. It also affects the variability. It may not affect the range. It may not affect the median. But every single score in your data set affects the mean and affects the standard deviation, and that's why they're used together. So in class, we will calculate the variance. It's the spread of scores, and then we'll get the standard deviation from that. So variance and standard deviation, I better just put variance here as well because that's a term we need to remember. And then finally, for today, let's talk about standard scores also. Standard scores allow us to make comparisons among variables and data that have different units. For example, if I want to compare 40-yard dash and maybe body weight, I want to say, okay, who's fastest? And I can't make those comparisons unless I have a standard score to compare body weight, which is in pounds or kilograms, and then speed. Well, that's in 40-yard dash is in 4.5, 5.5, whatever. And so I would have two different variables there, and it allows me to make comparisons between data sets that have different measurement units. That's the definition of a standard score. So if I'm in the 67th percentile in the bench jump, or I'm sorry, long jump perhaps, and then I go into something else based on body weight, do the bench press. Well, I'm only at the 50th percentile there. Compared to my peers, I did better on the first measurement, the bench, the long jump, the bench jump, or whatever, than I did on the second one. Okay, so that's the percentile rank. It's a standard score. You're compared with everyone else, and we make percentages. We do this all the time. We have percentile ranks for FitnessGram, although we don't use them. Especially we have them for President's Challenge, the Physical Fitness Challenge. We don't like to compare students, but they do have norms. And in the President's Challenge, you have to be at the, 85 percentile to get an award, and that's only about 15% of the people get that. And so again, percentile looks at everybody you're compared to others. Z-scores and T-scores, and you can kind of see these when we go back to the normal curve. The Z-scores can range from -3 to +3. And if you look here on 60, 59, 60, and 61, well, the Z-scores, you take a score from the mean, whether it's plus or minus, doesn't matter, and it's over the standard deviation. So it's the raw score minus x, x bar x, which is this symbol for the mean, over s, which is the subject, or n. Your book uses s quite a bit. And so to get the z-score, you take every single score, subtract it from the mean. So to calculate this, you need to have a measure of central tendency, and you need to have a measure of variability, the mean standard deviation. Okay, but the problem with z-scores is they can be negative, -3 to +3. And again, those are the same equidistant units that you see there on the normal curve on page 58. And now that explains the -3 to +3. Well, that's like a z-score. Okay, now t-scores, the advantage of t-scores is they get rid of that for you. So t-scores, take a z-score and figure a mean of 50 and a standard deviation of 10. But if you look at the -3 +3, all you have to do with t-scores is think of 50 in the middle, and then +1 would be 60, +2 would be 70, +3 would be 80. And then going the other way, -1, t-score would be 40, -2 would be 30, and -3 would be 20. And so the range on the normal curve of t-scores goes from 20 to 80, but it doesn't have any negative numbers, which is why they're used. And so now if you will look on page 64, you will see how percentiles set up with z-scores, t-scores, and percentile scales on a normal curve. And now you see all those standard scores. Notice how in the middle the t-score of 50 is equal to percentile scale of 50. Notice also in the percentile where it says +1, it is a t-score of 60, and then also 84.13. 84.13. How did I get to that? So if I'm at +1 on a t-score, or a z-score of +1, and I'm at 60 on the t-score, well, that's telling me that's equal to a percentile of 84.13. Quickly turn back to page 58 and look at the normal curve on 58. Do you see where the 0 is in the middle? And then going to +1, notice how between 0 and +1 there's 34.13. So if you add 50%, that's the 50 that's below, to 34.13, that's where you come up with that 84.13. And then if you look at +2 on that page 58, it has 13.59. Turn back to page 64, and you've added another 13.59 to that. And now if you're at +2 on the z-score, +2 on the t-score, you have a percentile of 97.72. In other words, if that's your score, give yourself a pat on the back, because you're higher than 97% of the people that took whatever that data test, whatever those scores are from. So again, you're better than 97%. That's how you interpret those tables and graphs there. And I'm going to stop with that. This is part 2 on statistics by Lacy, chapter 3. Thanks and have a great day.